Welcome to this session. My name is Renee McCormick, and I'm with the National Math and Science Initiative, and we are here today to work some thermodynamics problems. You're going to see some other skills woven into these, but that's good for you because that's the way AP problems work in general. So we're going to have a dash of stoichiometry, a dash of gas laws, and a bit of thermo. And so sometimes it's good news and sometimes it's bad news. And it could be good news if you're not so strong in thermo that there's still ways to make quite a few points on the thermo question, so you should not fear them. All right, let's get started. This one is from 1995, and propane, they tell us, C3H8, is a hydrocarbon that is commonly used as a fuel for cooking. Write a balanced equation for the complete combustion of propane gas, which yields carbon dioxide and water. Well, that's about as easy as the intro of an AP question is going to get. So they told us it's C3H8. And combustion, complete combustion, that's why it's making CO2, not CO, not carbon monoxide, is going to require oxygen, burning in air or such. And we're going to have CO2 and H2O as our products. This is a 9-point question, and you're about to see how easy it is to earn one of those points. So just dive in. I have 3 carbons. Let's give that a shot. Put a 3 there to make 3 carbons on each side. I have 8 hydrogens. The only source of hydrogen is over here at water, so I would need 4 because 4 times 2 equals 8, and leave oxygen or any plain element for last. So what have I got going on? I've got 3 times 2 for those oxygens on the carbon dioxide, so that's 6, plus 4 more because there's only 1 on each water. That's 10, so a big old 5 goes there. So I have a 1 to 5 to 3 to 4 mole to mole ratio. No phases were necessary to earn this point, and so you get a point for this. Then, the next thing they want me to do is probably use that equation in some form or fashion, because you should, by now, sort of be thinking the way I'm trying to train you to think, which is kind of let the problem lead you. So they now want us to calculate the volume of air. All right. We only used oxygen. So I must remind you that air is not entirely pure oxygen. That air is about 20-ish% of oxygen, and the remainder is nitrogen and other trace gases. So they want us to calculate the volume of air, not oxygen. You have to read the problem carefully. At 30 degrees Celsius. Well, I know that gases are involved here because it says and 1 atmosphere. So I'm going to take that 30 and go directly to Kelvin. Add 273 to 30, and I believe you come out with 303. And so now they've given me a pressure of 1 atmosphere, and I have a temperature, I feel Pivnert coming on, that is needed to burn completely 10 grams of propane, and assume that air is 21% oxygen by volume. So all I can do is calculate the amount of oxygen and realize that I'm going to need a whole bunch more air than what I actually calculate. So I'm going to take my calculation of the oxygen, which is the only thing I can do through Pivnert, and then I'm going to come back and inflate that by dividing my answer by the 0.21. That's what 21% translates into in decimal value. And that's going to make a much larger number, which will be the volume of air in liters that I need. All right, so off we go. First, I need to get that 10 grams business into moles, because I have a temperature, I have a pressure, they want me to solve for a volume, so I got the whole PV equals nRT thing going on. So let's get the molar mass for propane first. So that molar mass is going to equal 3 times, get your handy-dandy periodic table out, unless you've already memorized that carbon is 12.01, plus 8 oxygens at 1.01 each. I can do that in my head, 808, and add this together, and I'm going to get, well, I can do the first part in my head too. 36.03 plus 8.08. And I know you could probably do that part in your head too. 44.11 grams per mole. You should show that calculation because sometimes it's worth a point. And you never know whether it is or it isn't, but you needed it anyway, so you might as well scribble it down. And that way you may end up with a point just for being able to do that. So that means that the mole of propane is going to equal that 10 grams divided by that molar mass. And let me say something for the purists out there that might be listening. I realize that the way I'm supposed to do this is I'm supposed to look at the problem and say 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs, and I'm supposed to pull 3 sig figs off of the periodic table. So I shouldn't have used 12.01, I should have used 12.0 times 3. But you know what? I gave up that battle a long time ago. I just stick with 2 decimal places on molar masses and worry about the sig figs at the end of the problem, and I fall well within the range of what's accepted as a correct answer. So I don't waste time thinking too hard about how many sig figs to pull off of the bloody periodic table. I just go with 2 decimal places. So that's my disclaimer on that. All right, so when we do this, I'm going to take 10 divided by, grab that value up there, and I can do that because I'm on the new operating system for an 84. If you haven't upgraded the operating system, you should, because you're going to like it. And so we come out with 0.227. Yeah, that's right, 0.227 moles of oxygen. I remind you it's only oxygen, and we seek air. All right, so once you get to moles, you can do the stoic and look at the fact this is a 1 to 5 to 3 to 4 ratio and say, okay, if I have 0.227 moles of propane, I need 5 times that for the oxygen. So therefore, the moles of oxygen equals 5 times 0.227. Can't write today. It's going to be a long recording if that's the case. All right, so multiply what I got in my calculator by 5. And that's going to be the moles of propane required. Oh, this was propane. Sorry, that's what's messing me up. Please forgive. That could have led you astray. So now I'm looking for moles of oxygen. 5 times as much, sitting in the calculator, 1.13. That's what's required to burn up, to combust completely, that 0.227 moles of C3H8. So now I'm ready to actually use the Pivner and get to solving. So PV equals nRT, and I seek the volume of oxygen. I really seek the volume of air, but this is the best I can do for now. And so that's going to be nRT over P, so this is also moles of oxygen. So there is my 1.13 mole. My R, 0.0821, and my 303 Kelvin for my temperature. All that was given to me except for R. I should know R anyway. Notice I didn't put the units on R. Phooey. Liter, atmosphere, mole, Kelvin. So my Kelvins cancel and my moles cancel. And I want a liter in my final answer, so I'm putting a pressure in the denominator in atmospheres, which thankfully they gave me, and they made it easy on me. So hopefully you realize all you have to really calculate is your numerator. So therefore the volume of oxygen will come out in liters, and I will get... All right, let's have a moment about your calculator here for a second. You need to store R in your calculator. If you have never done that, then here's a new lesson for you. You need to say 0.0821 in your calculator, get it in there, and then this little button just above on that says store gives you a little arrow. It says what do you want to store it as. I would say R is an excellent idea, so hit your alpha key, and the R resides above the multiplication key, and hit enter, and then I like to test it. When I want to use R now, I just go alpha X, and I don't forget to type the 0, I don't get numbers backwards, and it's just faster. So indeed that looks like twice 0.0821, doesn't it? So I'm convinced it's working. So now here's how I use it in action. I go 1.13 times alpha R times 303, and I could beat you in this race. So I come out with 28.1 liters of oxygen. Therefore, the volume of air is equal to that 28.1 liters of oxygen divided by the fact that it's 0.21% oxygen. Let the problem lead you. And I come out with 134 liters of air required. And you don't have to put the required, I'm just doing that for your benefit. Okay, so for fun, let's talk about how many points we've earned so far, and we've done no thermodynamics on a thermodynamics problem whatsoever. I got a point for part A. Part B was worth 4 total points. Woohoo! A point for your ability to solve for moles using a correctly calculated molar mass, so a point for that moles of propane. A point for calculating the volume of the oxygen. So we get a point for the setup, I think it is. Yeah, for the, getting this concept back up here that I needed. Where'd it go? Ah, this multiplication right here. Using the stoic. So I'll put stoic. So a point for getting that 1 to 5 mole ratio and realizing that you needed to take the moles of propane and multiply it by 5 to get the moles of oxygen that you had or that were required. And then you get a point for the final answer and a point for the volume of the oxygen itself. So a point for using your PivNert and getting that, and then a point for realizing, well, I need way more air. And how do I deal with that? I deal with that 21% business. Okay, so there you have it. You've gotten over half of the points without doing any thermo. So now here comes the thermo. We'll go purple this time. All right, the heat of combustion of propane is, so this is delta H combustion. Calculate the heat of formation. So what do you want me to calculate? The heat of formation of propane, given that the delta H formation of water is thus, and the delta H formation of carbon dioxide is that. Well, if I look back at my balanced equation, they gave me the water, they gave me the carbon dioxide. Ooh, why didn't they give me the oxygen? Oh yeah, element, standard state, delta H, delta G, defined as 0 for that. So I don't need that. So this is an easy, greasy little Hess's Law moment. Big Mama equation, if you've listened to anything I've done before. So I'm just going to rewrite this because it's back up at the top of the page. This is what you wrote on part A. You don't have to rewrite it. I'm just doing it for clarity for our discussion here. And therefore, the delta H of the combustion for the reaction is equal to the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. And remember that this is 0 because it's an element in its standard state. So all of the gens, hydrogen, oxygen, nitrogen, and all the halogens are diatomic. So plug and chug. This is a negative 2,220.1. And I'm going to leave the units off because they're all going to be done in kilojoules per mole because I'm adding and subtracting here. So I'm just not going to muddy up my paper with a bunch of kilojoules per mole. Now, in class, of course, I would have you do that because you need good habits. But on the AP exam, you're in a hurry. So you just need to get at it. So 3 CO2 plus 4 of H2O's value. That's the sum of the products, minus, I only have one reactant to worry about, and that's what I seek, the delta H formation of C3H8. So I need to solve for that, move it over to this side of the equation. So the heat of formation for C3H8 is equal to, move the negative 2220.1 over by adding it. So 2220.1 kilojoules per mole plus 3 times the value for the carbon dioxide, which they gave me a negative 393.5, plus 4 times the value for the water, which was a negative 285.3, all in kilojoules per mole. So now it is a calculator extravaganza. Just punch everything in right. Plus 3 times the negative 393.5. Making sure I type everything right. Okay, plus 4 times a negative 285.3 equals negative 101.1 0.6 kilojoules per mole. That's about as easy as that's going to get. Okay, now what do I want? Now we're going to have some more stoichiometry fun, I think. Assuming that all of the heat evolved in burning 30 grams of propane is transferred to 8 kilograms of water with a specific heat, I feel Q equals MC delta T coming on, 4.18 joules per gram Kelvin, calculate the increase in the temperature of the water. So calculate the delta T out of Q equals MC delta T based on some thermodynamic concepts. So let's talk about those concepts. We're burning 30 grams of propane. Well, earlier we calculated the molar mass of propane. I remember doing that. And it was 44.11. So I don't have a full mole of this. So I'm going to have to deal with the fact I got to, calculate the mole business. So 44.11 molar mass, 44.11 grams per mole. Going to need that in a minute. And I know the mass of the water. That M is for mass, not for moles. And I know that my specific heat, this is my C, and Q equals MC delta T. Now, burning happens in an open container. Anything that you do in an open container is done at constant pressure, and that means that Q equals MC with a constant pressure notation on it, delta T, and that's going to equal, that means that Q also equals delta H. Okay, so I get to work from that. So the first thing I want to do is deal with this moles business. 30 grams of C3H8 divided by its molar mass of 44.11 grams per mole will get me moles of C3H8, lovingly called propane. And that is 0.680. That's 0.680 moles of propane, C3H8. Okay, so the first thing then I've got to realize is that I know delta H. I know that delta H is equal to that negative 2220. It's this delta H of combustion up here, right? Burning. See, they say burning, so it's combustion. So that means I know the amount of kilojoules. So therefore, I can do it over here under this one. Therefore, one more time. Q equals delta H equals that negative 2220.1 kilojoules per mole times the amount of moles I got, which is a fraction of a mole. Which is still sitting in my calculator, so just multiply it by the negative 2220.1, and I get negative 1509.9. kilojoules. That's how much heat is released in this burning business. So you want me to tell you how much the water increased? No problem. That's going to be, I'm going to rearrange my Q equals MC delta T up here. So the Q lost from the system of burning this C3H8 is equal to MC delta T. Therefore, delta T is equal to Q divided by MC. So I'm just going to plug and chug. I just got my Q, negative 1509.9, that's in kilojoules. My mass is 8 kilograms. Now, see how they gave me the C in grams? Yeah, you got to be on your toes with this stuff. So that's 8,000 grams, because I need my units to cancel. And so that's multiplied by the C value of 4.18 joules per gram Kelvin. And it doesn't matter if you do Celsius or Kelvin, because you're talking about a change, and the change on both scales is the same. All right, so we've got our negative 1509.9 sitting in the calculator, so let's simply divide that by this denominator of 8,000 times 4.18. As long as I got all that typed in right and close my paren, I should get the grand answer of, that did not come out what I expected. That comes out, what happened? I should get negative 45.15. What did I do wrong? Let's clear that and try again. Negative 15. Oh, see, you got me on your toes with this unit business. Okay, so there's a kilojoule, and then here's a joule. So let's make this joules, and then this stuff will work. There we go. So let's try that again. Negative 1509.9, make it joules instead of kilojoules, divided by, parentheses, 8,000. Sometimes I think it's good for you to see me mess up. That's my story, and I'm sticking to it. That makes more sense, because I knew when I got that first temperature, there's no way in heck I'm going to burn 8 freaking kilograms of propane and barely even warm the 8 kilograms of water. So, not 8 kilograms of propane, sorry, however many grams, 30 grams of propane. It's still going to make a pretty good fire that's going to warm 8 kilograms of water nicely. So it comes out to be a delta T of 45.15, and you could report it as Kelvin or Celsius, whichever one. Now, your math came out with a negative sign on it, but you know that a change in temperature is really an absolute value report. So I don't know for a fact whether they counted off or didn't give you the point if you had a negative sign on it, but I kind of doubt it. I bet they took it either way because they were so happy you'd gotten to the end of the problem. All right, so this piece was worth 2 points. Did I talk about the points on this piece? I did not. Let me go back up here and do that. Back up here, we got a point for the Hess's Law relationship. So I know you don't want to show your work. I get it. I'm a smart, lazy person too. I kind of pride myself in being smart and lazy. But I'm not stupid. So I know that I've got to either show it this way or this way. But somewhere, I got to show some work. I cannot just have an answer magically appear on the page with the AP exam and get all my points. Matter of fact, the work is worth more than the answer. And I had this conversation with a young man in Alabama last year. Brilliant child. Ended up making a 5 on the exam, but he had made a 2 on his mock exam, which is his practice exam in the spring before we get ready for the real deal. Because he could do all of his work in his head or in his calculator, he wrote nothing down but the final answer. And sometimes the final answer is not even worth a point. Sometimes it's the pathway that got there that has all the points attached. So I give you this speech because your teacher isn't crazy, and your teacher's not just being difficult, obstinate, or barbaric. They're actually trying to help you. So you really do need to show the work. So either way I saw Hess's Law on this paper, because I also scored these exams for several summers, then I'm not going to give you a point if you don't have Hess's Law in there somewhere. Some way I can identify sum of the products minus the sum of reactants with set equal to the heat of combustion. I got to find that someplace to give you that point. All right, then down here on part D, this part was also worth 2 points. And 1 point again. No, I take that back. Yeah, it's still worth 2 points, but 1 point for getting this value. Being able to realize that Q was delta H and that you had a fraction of a mole, so you weren't going to have negative 2220.1 kilojoules. You were going to have that times the fraction that you had of 0.68. So getting that number was worth a point. And then the final answer was worth a point. Okay, so as you can see, half of this was about gas law, stoichiometry type basic skills. The other half was really about the thermo. The one we do next, it's all about the thermo. So this is kind of a nice intro to kind of polish up some of your skills. So we're going to move on to the 1998 problem. I'm going to make a copy. I've learned this lesson the hard way. I'm going to make a couple while I'm at it. All right, so I fixed a typo on this file, and I did not know this until I was working these out and getting ready to do these with you. There was a typo in this table because a lot of this stuff is old, from 98, as you can imagine. So all I had was like a hard copy, and to scan them in is all ugly, so I retyped them. or have them retyped by someone in my office. And it happens. It's easy to mistype a number, especially when you're looking at the number and you're trying to get it in there, and it's the difference between negative 395.5, because a 0.5 comes after, and negative 393.5. So by now, you know that you're supposed to work these ahead of me. I already did that. It was a note to myself. And you have probably worked it with the typo. And so I'm going to share with you both answers. But if you have recently gotten this off of the wiki page, or if you're a teacher listening and you've recently gotten it off of your site, then the typo has been fixed. So for future reference, there is a typo on the worksheet, but it's been fixed. Kind enough to give me a balanced equation with a 1 to 7 to 6 to 3 ratio if I need that for stoic later. I've been given delta H formations and entropies. I haven't read the problem yet. I like to examine what the story is first. I'm looking at solid plus gas, so I have 7 moles of gas going to 6 moles of gas and 3 liquid. And if this is going to be at a really high temperature, I'm on the lookout for this water vaporizing. So if we're talking about high temperature over 100 degrees Celsius, then I'm expecting that 3 liters of liquid water to actually become 3 liters of water vapor, in which case my delta S would be positive. As it stands right now, it's going to be negative due to the decrease in the number of moles of gas and the fact that I also had a mole of solid. So I'm just thinking ahead here. And then, what else do I know? Okay, I guess I can actually read the problem now. When a 2-gram sample of pure phenol, C6H5OH, solid, is completely burned, combustion, we love combustion in thermo, according to the equation above, 6.498 kilojoules of heat is released, therefore delta H is XO, because released means that. Therefore, delta H is equal to negative, I must supply that, 64.98 kilojoules per mole. And this is a delta H of combustion. Sorry, that's a little messy, but you get the idea. So, what else do they want? They've given me this table. I remind you there's a typo right there, 393.5. Everything else was correct. So, first thing is calculate the molar heat of combustion of phenol in kilojoules per mole at 25 degrees Celsius, which you will immediately take to 298 Kelvin, in case you have gas law moment coming up. All right, so how much did I burn? 2 grams. That's a lot of sig figs, isn't it? 2 grams divided by the molar mass, which I need to come up with. I don't think they gave it to me. I'm looking. Nope, got to come up with that. So, molar mass is going to come out in grams per mole, and it's going to be 6 times 12.01 plus, I've got 6 total hydrogens. See them? 5 there, 1 there. 6 times 1.01 plus 16.00, if you must. All right. Equals. And I'm going to write that molar mass down, because I might need it later. If I'm going to work it out, I'm on the lookout for the fact I may need it later too. So 6 times 12.01 plus 6.06 plus 16 equals 94 grams per mole. All right, so 2 divided by, go up and grab it, put it in, execute the command. So I have 0.0212 moles of phenol. That was actually worth a point doing that calculation. It's always good to show that. Therefore, the delta H of combustion is equal to the 64.98 that they gave me. Kilojoules per mole divided by the fact I only had 0.0212 measly moles. Cancel, cancel. All right, so negative is 64.98 divided by, go and grab it, paste it, execute the command. Negative 3058, I'm going to call that. And don't leave it naked. Naked numbers are disgraceful. Kilojoules per mole. There you go. So they were kind to you on this one and gave you that point for just the value, with or without units. But we do expect to see that negative sign on there because it is a combustion. And for the crying out loud, it's a combustion. You're burning something. Don't you think it gets hot? And if it gets hot, that means it's giving off heat. It's giving off heat energy. It's losing heat energy to the surroundings, hence the negative sign. All right, then. Calculate the standard heat of formation of phenol in kilojoules per mole. Okay, when they use this little F, it's always the formation of 1 mole. But you know what? They balanced our equation for us, and they were very kind to us and gave us 1 mole. Not all problems will do that. So you may have to write a heat of formation reaction that would be with elements, and you may have to use fractions. So let me explain what that means. So I'm going to take a little diversion here. C6H5OH. If I write the heat of formation reaction, I need to, by definition, form 1 mole. How much? 1 mole. How much? 1 and only 1 mole of this stuff from the elements in their standard states. So carbon in its standard state is a solid. Hydrogen is diatomic because it's a hydrogen, and it's a gas at standard state. And oxygen, also a gin and a gas at standard state and diatomic. So now, in order to balance this equation, that's easy enough. Put a 6 there. I have 6 total H's. Be on the lookout for the fact they're in 2 places. So I need a 3 there to get 6. But I only have 1 oxygen. And I cannot come over here and like double this and then go back and double everything else. By definition, I'm forming how much? 1 mole. So I need to put a half in there. Because this problem didn't ask for that with that concept, but you know what? We do this a lot in the multiple choice, and I want to make sure that you're clear on it. So this is an easier problem. I'm just going to use the Big Mama equation and use the balanced equation they gave me and calculate this value right here. So that's going to be a 0. It's the only element I have. So this is going to simplify out to delta H combustion is equal to the sum of the delta H of the products minus the sum of the delta H of the reactants. So what does that translate into? Looking at the top of the page at that balanced equation, that's going to be 6 times CO2's value plus 3 times water's value. Again, looking at the balanced equation they gave you at the top of the page, minus what we seek, which is the C6H5OH value, plus 7 times oxygen's, but that becomes a 0. How come? Element in standard state. That should give you a little sort of a happy dance moment when you get to neglect something in your calculation. So this translates with numbers into negative 3058 or whatever you calculated. So let's say you screwed up here, you didn't get this negative 3058 kilojoules per mole. It's okay to put in scientific notation too, 3.058. I would even take 3.06 at this point, as long as it's in kilojoules per mole. So when you have that, whatever you got there, bring it down here. So you can recover all of the points on part B, even with a wrong part on part A. It's called consistency. As long as you're consistent with your numbers and you know the concepts, we'll give you the points. So 6 times, go look at the table. Look in the proper column of the table. This is where the goof happened. 393.5. You may have worked it as 395.5 because that's what was printed on the page because of the typo. Plus 3 times a negative, and that was a negative, by the way, a negative 285.85 for the water. See? Check, check. Minus what we seek, C6H5OH. I'm going to put delta HF. I should have done that up here too. So delta H F of C6H5OH. All right, so this is what I want. I'm just going to move that over. And let's do the math. So I've shown the setup. I don't have to like write it all out again. I'm just going to solve for what I need. So I'm moving this over. Doesn't that mean I add this into the situation, this negative, to move it over? So just doing some 8th grade algebra here. So I'm going to get 3058 plus 3 times a negative 285.85 plus, oh, was that it? Hey, that was it. That's all I needed. So delete that plus. Enter. I skipped over one, didn't I? Because that's not right. Okay, so that value, I went to the water instead of doing the other first. So that's supposed to be plus. Let me start again. I'm all messed up now. All right, let's try that one more time. I'm going to move the 3058 over to the right side of the equation, which makes it positive. Okay, so now that is added to 6 times, I think this is the part I skipped a minute ago, 393.5. And again, you might have used 395.5. I'm aware of that. Plus 3 times a negative 285.85. And I bet it works out right this time. Ah, there we go. All right, so what you should have gotten without the typo was a negative 161 kilojoules per mole. That's without the typo, using negative 393.5 for the CO2. But with the typo, I worked it out both ways, you get negative 172 kilojoules per mole. With typo of negative 395.5 for the carbon dioxide. So I apologize. It's fixed now. All right, so what were the points on this? Did I write them down? There were 3 points associated with this. 1 point for getting the stoichiometry and the substitutions correct. So getting the 6, getting the 3, putting them in the right spots. And yes, it's commutative across that plus sign. So you could have done 3 waters and 6 CO2s, same thing. 6 of one, half dozen of another. So 1 point. And then for that, a point for getting the sign and a point for the value. So this, which is the correct answer without the typo, with the actual equation, question as it should have been typed. So 1 point for the sign. In other words, you're going to lose that point if you didn't put the negative. And then 1 point for the value, or the magnitude if you wish. Okay. Now, calculate the value of the standard free energy change, delta G, for the combustion of phenol at 25 degrees Celsius. Okay. Did you not feel that coming? Because they gave you the delta H's, they've given us the delta S's, and now they want us to use the granddaddy equation, the Gibbs free energy equation, and calculate delta G. So to do that, I've got to think through the fact that delta G equals delta H minus T delta S, but dang it! I don't have the delta S value, but I have the means in the table by which to obtain it. So there's more math in my future. That's why this is a problem, and it's why you have a calculator in your hand at the time. All right, let's go green for this one since it's delta G. And I'm understanding that I need delta G equals delta H minus T delta S. And I've been a little sloppy with my signs here. I'm all fixed up now. All right, so calculate the value, and I need the delta S. So delta S naught, I need that value. And that is equal to, again, the same Hess's law setup that you just had up here at the top, except you do have to put in the oxygens because, aw shucks, it's delta S, and you've got to have a value for that because the only thing that is 0 delta S, or 0 S, just 0 entropy, is going to be a pure crystal at 0 Kelvin, which we don't have and we're not at. So I've got to set this up. I need 6 times CO2's entropy value plus 3 times water's entropy value. That is the sum of the products. And I'm not going to write that down again because I've kind of shown my ability to do this up front. But just for clarity, this is the sum of the delta S, not H, delta S of the products minus the sum of the delta S of the reactants. And we are at standard conditions, so we need the noughts. All right. I don't get to neglect anything for this one. This is the C6H5O60H. Let me try that again. OH plus 7 times O2. Where'd I get the 7? Balanced equation, top of the page. All right, so now let's plug and chug. See if we can plug this in right. This is 6 times 213.6. Reading it off of the table. 213.6 for the carbon dioxide. 3 times water, which is 69.91. Again, off of the table. So get that. Minus the value of 144 plus 7 times oxygen's value, which is 205. Okay, equals, we get a clear screen for this one, 6 times 213.6 plus 3 times 69.91. I'm going to get that piece. Minus, I'm going to open a couple of parens. I probably only need one, but it's too late now. I've made a commitment. 144 plus 7 times 205. I'm close both of them, it won't matter. And I get a negative value, a negative 89.47 joules per mole Kelvin. Because S's, if we look back up here at the table, are done in joules, while H's and G's are done in kilojoules, and that always wreaks havoc with you in terms of remembering that. Okay, maybe when I said you, I meant me. So I get a negative 89.47 joules per mole Kelvin, but I'm nowhere near finished with this problem. The good news, however, is I do get a point for that. And that was a lot of work for 1 point. Dang it. So now calculate the delta G. Delta G equals delta H minus T delta S, which you just took all that time figuring out. The rest you already knew. And so that means that delta G naught equals a negative 3058 kilojoules per mole minus 298 Kelvin times the value that you just did, but put it in kilojoules because you cannot subtract a joule from a kilojoule any more than you could subtract a yard from an inch. So I've got to get these both in kilojoules. So negative 0.08947. 1, 2, 3. Yes, that makes that kilojoules per mole Kelvin, so that my Kelvins cancel. Nice how that works out. Equals. Where did I get these numbers? The 3058. Didn't we solve for that? Yeah, way back up on part A. So they led me to get delta H combustion for this reaction with the 2 grams of the phenol. And so I use that value. And then I had to go and get the delta S myself. And remember the fact this is all done at standard conditions. So I come out with, I'm going to divide that by 1,000. So instead I divide by 100. So let me divide again by 10. I missed a 0 when I was typing. There. Okay, so negative 3058 minus 298 times, and now I'm going to go grab that. Never be a quitter, always go to. I see what happened. I don't even need that paren, as it turns out, so there we go. So you should come out with negative 3,031. My negative didn't write. Negative 3,031 kilojoules per mole. Also worth a point. So this whole piece, which was actually quite a bit of work, was only worth 2 points. All right, so what did you get the points for? 1 point for the answer and 1 point for calculating delta S. Now, 2 points for this piece. If the volume of the combustion container is 10 liters, calculate the final pressure in the container when the temperature is changed to 110 degrees Celsius. Assume no oxygen remains unreacted and that all products are gaseous. Sounds like, feels like, could be. Ideal gas law. Your good buddy Pivnert. All right, so looking back up at the top of the page, this was what I warned you about in the beginning. If they went over 100 degrees, I was expecting that liquid water, the 3 moles of liquid water, to become gas water vapor, is the technical term. So note that the 110 is above that boiling point, and all of the products are going to be gaseous, so we have 9 moles of gaseous products. So let's review this equation real quick. We had, and you don't have to write this down, okay? I'm just going to do it for clarity for you. C6H5OH, which is my phenol. And that is reacted with 7 moles of oxygen once we balance the equation, or they gave it to us, I can't remember now, and 6 CO2s and 3 waters. So this is now gone because it's completely combusted. So I now have everything converted because it said assume that no oxygen remains, so that's now gone. So I have 9 moles of gas. Now, if I go back to the fact that I had a 1 to 7 to 6 to 3 mole to mole ratio, and I'm just combining this into total moles of product, instead of worrying about the fact that 6 of them were carbon dioxide and 3 of them were water, I need to go way back up and find that number of moles that I started with. The 2 grams divided by the molar mass was 0.0212 moles. 0.0212, 0.0212, 0.0212 moles. Therefore, the total moles of gas is equal to 9 times that value. That was the sticking point on this problem, is realizing, dear God, I've done so much, I forgot what those moles were, but you did it back on part A, you get to use it again. So that's going to be my moles of gas in my Pivnert equation. So now we can get on with that. PV equals nRT. What do they want me to solve for? All right, I got a volume of 10 liters. I've got a temperature of, what is that going to be, 383? Yeah, 383 Kelvin. 273 plus 110. Yep, 383. So there's my temperature. So I've got a T, I have a V. They want me to solve for P. I know R. I needed this N, which I just figured out. So therefore, P equals nRT over V equals 9 times 0.0212 moles, 0.0821 liter atmosphere mole Kelvin, and the kelvins, the temperature, were 383. Kelvins cancel, moles cancel. Once I put this atmosphere down here, what was the pressure? Oh, wait, that's what I'm looking for. Once I cancel out the liters, I'll get atmosphere. So volume was 10 liters. So that liter cancels that liter. I'll come out with an answer in atmospheres. It's worth going to the calculator now. So 9 times 0.0212 times alpha R times 383, get my numerator, divide it by 10, and I come out with, that's a number really, really close to 0.6. So 0.600, 3 sig figs seems to be the flavor of this problem. And don't leave it naked. What's it going to be? That would be atmospheres. All right, so that was worth a point, getting that. And the other point came from the stoich. So yes, if you missed out on that multiplying by 9 business and whatever you used for moles is plugged in over here, so whatever you've got in this spot right here, as a grader, I would pick up my calculator and take that times 0.0821 times 383 and divide it by 10, and if I came out with the answer on your page, I would give you this point. You would have lost the point for the stoich, but you would have gotten that point. So sometimes some of the easier pieces of an AP problem come at the very, very end. All right, so let's look at one more before we finish up this recording, and then I have good news for you. If you dare to hang with me and go through the next recording, which will be part 2 of the problem solving for Thermo, there's only 2 more left. So we're doing the worst of it now with 3. So moving onward, we're going to go to 1998. Oh wait, that's what we just did. Sorry, we're going to go on to 2003. Yeah, 2003B. B means it's the exam that's given across the international date line because you little buggers cheat. 10 points on this one. In an experiment, a sample of an unknown pure gaseous hydrocarbon was analyzed. Results showed that the sample contained 6 to 4 significant digits grams of carbon and 1.344 grams of hydrogen. This is the good old hydrocarbon is all that's in there, just H's and H, X, C, Y. We're looking for the X and the Y. And we know that I have carbon and then I have hydrogen. They didn't even try to trick me with water. So can you calculate the number of moles is what this boils down to here in the beginning. Determine the empirical formula of the hydrocarbon. Formulas are a mole to mole ratio simplified, since you can't have fractions of atoms. So I've got the 6.000 grams of carbon divided by its molar mass of 12.01 grams per mole equals, that's dang close to a half, isn't it? 0.5000 moles of carbon. If I didn't put the 01. And I think it may even round to that even if you do, but I'm going to call it 0.5 because that's just awfully close. 1.344 grams of hydrogen divided by 1.01, going to come out really close to 1.333. So I'll do it just for fun, but 1.33. That I could just tell is a third. Hello, it was 1.34 to begin with. It's going to be 1 point slightly less, 1.33 moles of hydrogen. This is not something you would write on your paper, but just in case you're a little fuzzy on empirical formula stuff, we're talking now that we have figured out it's C.5 H1.33. But we never write formulas that way. So I'm going to have to get rid of these little annoying fractional decimal place kind of subscript things. So you just, process of elimination comes to mind. If I double everything, will that do it? Well, it'll double the 0.5 to 1, peachy, but the 1.33 will become 2.66, so crap, no. So do I triple it? Will that work? Well, what do you get if you do that? If you do that, you're going to get well, let's try this. Let's try simplifying the 1.33. So if I divide both of them by the same number, if I divide them both by 0.5, I come out with 2.66. That's not better. So what to do next? Well, if I triple it, if I triple the 1.33, and I must triple this as well, then I get 1.5, and I get somehow I get C3H8. Multiplying both by 3, I get C3, because that's going to be C3H8. I don't think that's right. I think I have to multiply them both by 6. .33 times 6 equals
Yeah, that's what I've got to do. Because just doubling, it's just process of elimination. Did doubling work? Did tripling work? Did quadrupling work? Did multiplying by 5 work? No, I had to work my way all to multiplying by 6 to get both of them to whole numbers. I thought 3 was going to do it for H, but it didn't do it for carbon. So I have to keep going to 4, to 5, to 6. A little bit of number sense here. So we come out with, and I'm not going to use that as an equal sign. I'm going to use an arrow that leads us to C3H8. That is the simplest formula that I can come up with. And that's my empirical formula. All right, so now the density of the hydrocarbon at a temperature of 298 Kelvin, there's a pressure, there is a density. Do you know any relationship that you've learned in class with gas laws that is going to get you the molar mass of this substance based on its density? Molar mass of a gas, so this gas. So you got to feel like PivNert's involved somehow. And you can do PivNert, and you can rearrange, and you can get N over V for the volume, I mean the density piece of it, or you can give up and memorize what we lovingly call the molar mass kitty cat equation. If you want molar mass, and you have the density of the gas or the means to calculate the density of the gas, they give you a grams and a volume in liters, or a volume in anything you can transform to liters, then every good cat puts dirt over its pee. Those of you that are cat lovers out there already know this. So we've lovingly called this the molar mass kitty cat formula. So I can take that density of 1.96 grams per liter, multiply by liter, atmosphere, mole, Kelvin, multiply it by R, and 298 Kelvin, and divide it by the pressure of 1.09 atmosphere. Before you pick up the calculator, let's do the units. Liter, liter, Kelvin, Kelvin, atmosphere, atmosphere, grams per mole. Isn't that what molar masses are measured in? Now it's worth using the calculator. So the molar mass is equal to 1.96 times alpha R times 298 equals, divided by 1.09, equals 21.54. What happened? That's not right. Let me try that again, because it's supposed to come out like 44. So I may have mistyped something. 1.96 grams per liter times alpha R times 298, enter, divided by 1.09. I must have mistyped something the first time, because this is going to work. Okay, so 44. I'm going to put a 0.0 on it, because that's really close to being just flat out even 44 grams per mole. And they want me then to do the classic, I got you to get a molar mass, you got you to get an empirical formula, now let's do a molecular formula. So the molecular formula has, or the empirical formula has an empirical mass. So C3H8 empirical mass equals, and I'm 3 times 12, I'm just going to do this one rough, plus 8 times 1. So that's 36, and 8 is 44. 44 grams per mole. Therefore, C3, well, which is the, I'll say which is the molar mass. Therefore, C3H8 is the molecular formula. Okay. I don't need it to go that way. There we go. Okay, in another experiment, liquid heptane, C7H16, is completely combusted to produce carbon dioxide and water, as represented by the following equation. God, love them for balancing it. Let's go purple. 1 to 11 to 7 to 8 if I need that. The heat of combustion, not the formation, of 1 mole for 1 mole, well that's nice because that's going to make my math easier, C7H16 is, using the information in the table below, calculate the delta HF for. Okay, so this is the classic, the delta H combustion is the delta H of the reaction, because this is a combustion reaction, go figure. And so I am looking for one of the pieces. And so I've got delta H not combustion, and it's a Big Mama Hess's Law moment, is equal to the sum of the products, which is 7 times the CO2 plus 8 times the H2O. That's my products, minus the sum of the reactants. Hallelujah, that's a 0. We've seen this skill before in this recording. So C7H16 delta H is what I seek. All right. So now let's plug in the numbers. Negative 4850. Where'd I get that? They gave it to me in kilojoules. I just took it out of scientific notation. Equals 7 times a negative 393.5 minus 8 times a negative 285.8 plus, minus delta HF that I seek. All right, so it's the classic move that delta HF over to the right side of the equation and move the negative 48.50 over to the, I said that wrong. Move the delta HF over to the left side of the equation, take the negative 4850 kilojoules and move it over to the right. And I know that all this is coming out in kilojoules per mole, so I'm sloppy with my units on this. But let's do it. So I've got 4850 plus 7 times a negative 393.5 plus, I wrote a minus, but it's plus 8 times a negative 285.8. Enter. So I'm going to call it negative 191 kilojoules per mole. And that was C7H16. And there you have it. And then I've got less than a mole. I've got a very small sample, a 0.0108 mole sample of this stuff combusted in a bomb calorimeter. All right. Normally, we do Q equals MC delta T. But in a bomb calorimeter, this is combined into Q equals C delta T, big capital C. Because the mass of the container and the specific heat of the container is the bomb, and the bomb is a structure that we know, and so we just stamp it right there on the device, and there you have it. That's the combo of its mass and its actual amount there. So, given the total heat capacity, calculate the amount of heat released. So that's a, better have a negative sign on that delta H when you're done. The heat released then is going to be the fact that delta H is equal to how many moles we had, 0.0108 moles of C7H16 times the negative 4850 kilojoules per mole they gave us as the heat of combustion for this stuff. So 0.0108 times a negative 4850 gives me a negative 52 point, let's call it 4 kilojoules per mole. And that's equal to Q. How come? Because we stayed at constant pressure. So given that the heat capacity of the bomb, or the total heat capacity of the calorimeter is what I should say, is 9.273 kilojoules Celsius per Celsius. Calculate the temperature change of the calorimeter. All right, so like I said a minute ago, Q we normally deal with as MC delta T, but when you know the total heat capacity for the bomb, it combines and we get C delta T, and in this case, all that's also equal to delta H that we just calculated. So delta T is going to be equal to delta H over that big capital C, which is the 52.4 degrees, and it's a change, so I don't even need to worry with the sign. Kilojoules, not degrees, sorry, that we just calculated, divided by the 9.273 kilojoules per degree C, the units on that constant. So divided by, what's sitting in my calculator, divided by 9.273. And so this is a negative, well, it doesn't have to be a negative, it's a delta T, of 5.65, 5.648, 5.65 works, degrees C. So it was a combustion, it got hot, therefore the temperature increased, so we would have a positive sign on the delta T from common sense. All right, I don't think I talked scoring on this, so let me just double check and make sure that you are clear on what you got scored for. So back up here on part A, we got a point for getting this ratio. So a point for the ratio. A point for realizing I got to go all the way to 6 before I get this to work out into whole numbers. So I get a point for that. So that whole part was worth 2 points. Then I get a point for getting that molar mass on this, and a point for the substitutions. In other words, showing your work. Even if you made a math mistake, you'll still get a point. And then a point for stating that this was the complete molecular formula is the words I'm struggling for, molecular formula, and however you verified it. You don't have to verify it the way I did. There's other ways. So you have to have a verification there. Then, on this piece, a point for the correct use of coefficients. So getting your 7 and your 8 into your Hess's law calculation. And again, you don't have to make it look like mine, but you got to get it in there somehow. And then a point for the actual answer. So you can't just put the answer and earn 2 points. You must show work, must show work, must show work. And then this, which I did not box, was worth a point. And then the final here was worth a point. So thank you so much for your kind attention, and there are only 2 more free response problems for us to work through, so I will do that in another recording. I hope you have a great rest of your day.